This is one of my favorite examples because it shows the ridiculous power of the LAB color model. Moreover, it looks quite exceptional in this case because it doesn't involve any conversion of the original image to LAB, as I said in the introduction. The LAB rules are somewhat tough to remember, but believe me, when you finally start thinking in LAB, it becomes second nature and life will be a lot simpler. In a nutshell, it goes like this. LAB has three components like RGB, but their nature is substantially different. L stands for lightness and tells us if something appears either dark or light, regardless of its color. L doesn't know anything about something being orange, purple or green, because it doesn't carry any information about either hue or saturation. It just tells us how light a color is. A and B are in charge of color instead, but ignore lightness, which is encoded in the L component only. A tells us whether a given color is biased towards either green or magenta. B tells us whether the color looks either blue or yellow. So yes, there are two colors called opponent colors in each chromatic component of LAB. In order to accommodate two colors in one component, the A and B components have a unique behavior. They can be negative, and this is unique because it makes no sense to think of negative RGB components. When an RGB component is 0, it means that the light of the corresponding color is turned off. You cannot have less luminance than that, so negative values are meaningless. Negative numbers have no meaning either in CMYK, and even the L component of LAB can have values between 0 and 100, so it's always positive. The rule of thumb for the A and B components is simple. Both A and B are split in two and have a cold color component and a warm color component. For A, the cold component is green. For B, it is blue. Magenta and yellow are the warm components of A and B respectively. When the component is negative, the color shifts towards the cold primary. The opposite happens with positive numbers. Hence, a negative value of A points to the fact that the color is shifted towards green, whereas in B it declares that it is shifted towards blue. A positive A component screams, "I am magenta," and in B, "I am yellow." It should be clear that while a color can have both A and B positive, for example, and this would produce some kind of red, which is at the same time shifted towards magenta and yellow, it is impossible for a color to be at the same time blue and yellow or green and magenta. An important point is the zero, which divides negative and positive numbers in two. If a color has A equal to 0 and B equal to 0, it is neither green nor magenta, neither blue nor yellow. Since repeating this statement every time would quickly bring us to insanity, we call this color neutral and realize it's some kind of gray. Which gray? Well, dark if the L component is low, light if it is high. L equal to 0 corresponds to pure black. L equal to 100 to pure white. In this picture, you can easily spot a serious blue cast in the hair of my son, and on the jacket collar too. Welcome to the maddening world of double casts, or even multiple casts, which happen when two or more different light sources with a different color temperature hit the subject. In this case, I had no choice. The white band you see on the left is actually a window pane. The light from the outside had the typical color temperature of daylight, around 6000 K. The main light inside the room, a lot weaker, was produced by a tungsten lamp whose color temperature is around 3000 K. In practical terms, the light inside the room was orange with respect to daylight, or, if you prefer, the light from the sun was a lot bluer than the main source. The window pane appears white because the light was so strong for the exposure I set that everything was blown out at sensor level. This is the phenomenon of clipping. The photosites overload, and all they can say is, this is pure white, although our eyes would perceive something instead. The behavior of LAB curves can be surprising if you're not acquainted with them. If you use the L curve, you'll see the lightness change while the color remains identical. If you click to set a point and push it up, the image will become lighter. If you pull it down, darker. You can always reset the curve by clicking on the Reset button. If you use the A curve, pushing it up will make the image more magenta, while pulling it down will give it a greener look. Notice that the color changes, but the lightness is untouched, because both the A and B components do not carry any information about it. As you may surmise, the B curve behaves similarly to the A curve. Pushing it up shifts the picture towards yellow, pulling it down towards blue. In LAB curves, you usually want to keep some points steady. Let me show you a very interesting thing. The light coming from the window is pure white. This means it has no hue. Its value is 0 both in the A and B channel. If we use the color picker to sample that area, the color picker itself will show an LAB readout of 100, 0, 0. This is pure white indeed, maximum lightness, no hue. We are currently working on the B curve, responsible of the blue-yellow component of LAB. If we click on OK, we see that the point is created in the middle of a curve. The middle of a curve corresponds to value 0. Negative numbers, which are related to blue, are below, while positive numbers related to yellow are above. The skin tone contains a yellow component, so it's easy to imagine what will happen if I sample it. The corresponding point is created above the previous one in the curve. On the contrary, the blue cast should create a point below. Let's see. This is exactly what happens. The idea now is to push the lowest point up so that the blue hue shifts towards yellow. The aim is to find a balance which will kill the blue cast and make the hair and the jacket look correct. And I guess this is it. It should be clear why we need to set 2 points, one for neutrals and one for the skin tone. Without them, the whole curve would go up and the whole image would get yellow. So, these 2 points are what we might call pivot points, which have the purpose to keep the correct colors from shifting. LAB is very powerful and very selective at the same time. If we go too far with the correction, the blue cast would turn into a vividly yellow one. If we pull down rather than pushing, the blue cast gets worse, transforming the kid into an alien with radioactive hair. The next example is devoted to matching the color between images which look different but should look similar instead.